1.4.3 Evaluating composite functions. Once we compose a new function from two existing functions, we need to be able to evaluate it for any input in its domain. We will do this with specific numerical inputs for functions expressed as tables, graphs, and formulas, and with variables as inputs to functions expressed as formulas. In each case, we evaluate the inner function using the starting input and then use the inner function's output as the input for the outer function. A. Evaluating composite functions using tables. When working with functions given as tables, we read input and output values from the table entries and always work from the inside to the outside. We evaluate the inside function first, and then use the output of the inside function as the input to the outside function. Example 5. Using a table to evaluate a composite function. Using Table 1, evaluate f of g of 3 and g of f of 3. Table 1. For x equals 1, f of x is 6, and g of x is 3. For x equals 2, f of x is 8, and g of x is 5. For x equals 3, f of x is 3, and g of x is 2. For x equals 4, f of x is 1, and g of x is 7. Solution. To evaluate f of g of 3, we start from the inside with the input value 3. We then evaluate the inside expression g of 3 using the table that defines the function g, such that g of 3 equals 2. We can then use that result as the input to the function f, so g of 3 is replaced by 2, and we get f of 2. Then, using the table that defines the function f, we find that f of 2 equals 8. G of 3 equals 2. F of g of 3 equals f of 2 equals 8. To evaluate g of f of 3, we first evaluate the inside expression f of 3 using the first table, f of 3 equals 3. Then, using the table for g, we can evaluate g of f of 3 equals g of 3 equals 2. Table 2 shows the composite functions, f, composed with g, and g, composed with f, as tables. Table 2. X equals 3. G of x is 2. F of g of x is 8. F of x is 3. G of f of x is 2. Try it number 3. Using Table 1, evaluate f of g of 1 and g of f of 4. B. Evaluating composite functions using graphs. When we are given individual functions as graphs, the procedure for evaluating composite functions is similar to the process we use for evaluating tables. We read the input and output values, but this time, from the x and y axes of the graphs. How to. Given a composite function and graphs of its individual functions, evaluate it using the information provided by the graphs. 1. Locate the given input to the inner function on the x-axis of its graph. 2. Read of f the output of the inner function from the y-axis of its graph. 3. Locate the inner function output on the x-axis of the graph of the outer function. 4. Read the output of the outer function from the y-axis of its graph. This is the output of the composite function. Example 6. Using a graph to evaluate a composite function. Using Figure 1, evaluate f of g of 1. Figure 1, a. X, g of x. Figure 1, b. X, f of x. Solution. To evaluate f of g of 1, we start with the inside evaluation. See Figure 2. Figure 2. X, g of x. 1, 3. G of 1 equals 3. X, f of x. 3, 6. F of 3 equals 6. We evaluate g of 1 using the graph of g of x, finding the input of 1 on the x-axis and finding the output value of the graph at that input. Here, g of 1 equals 3. We use this value as the input to the function f, f of g of 1 equals f of 3. We can then evaluate the composite function by looking to the graph of f of x, finding the input of 3 on the x-axis and reading the output value of the graph at this input. Here, f of 3 equals 6, so f of g of 1 equals 6. C. Analysis. Figure 3 shows how we can mark the graphs with arrows to trace the path from the input value to the output value. Figure 3. X. G of x. Figure 3. X. F of x. Try it number 4. Using figure 1, evaluate g of f of 2. D. Evaluating composite functions using formulas. When evaluating a composite function where we have either created or been given formulas, the rule of working from the inside out remains the same. The input value to the outer function will be the output of the inner function, which may be a numerical value, a variable name, or a more complicated expression. While we can compose the functions for each individual input value, it is sometimes helpful to find a single formula that will calculate the result of a composition f of g of x. To do this, we will extend our idea of function evaluation. Recall that, when we evaluate a function like f of t equals t squared minus t, we substitute the value inside the parentheses into the formula wherever we see the input variable. How to? Given a formula for a composite function, evaluate the function. 1. Evaluate the inside function using the input value or variable provided. 2. Use the resulting output as the input to the outside function. Example 7. Evaluating a composition of functions expressed as formulas with a numerical input. Given f of t equals t squared minus t and h of x equals 3x plus 2, evaluate f of h of 1. Solution. Because the inside expression is h of 1, we start by evaluating h of x at 1. H of 1 equals 3 times, open parenthesis, 1, closed parenthesis, plus 2. H of 1 equals 5. Then f of h of 1 equals f of 5, so we evaluate f of t at an input of 5. F of h of 1 equals f of 5. F of h of 1 equals 5 squared minus 5. F of h of 1 equals 20. E. Analysis. It makes no difference what the input variables t and x were called in this problem because we evaluated for specific numerical values. Try it number 5. Given f of t equals t squared minus t and h of x equals 3x plus 2, evaluate. A. H of f of 2. B. H of f of negative 2. 1.4.4. Finding the domain of a composite function. As we discussed previously, the domain of a composite function such as f, composed with g, is dependent on the domain of g and the domain of f. It is important to know when we can apply a composite function and when we cannot, that is, to know the domain of a function such as f, composed with g. Let us assume we know the domains of the functions f and g separately. If we write the composite function for an input x as f of g of x, we can see right away that x must be a member of the domain of g in order for the expression to be meaningful, because otherwise we cannot complete the inner function evaluation. However, we also see that g of x must be a member of the domain of f, otherwise the second function evaluation in f of g of x cannot be completed, and the expression is still undefined. Thus the domain of f, composed with g, consists of only those inputs in the domain of g that produce outputs from g belonging to the domain of f. Note that the domain of f composed with g is the set of all x such that x is in the domain of g, and g of x is in the domain of f. A. Domain of a composite function. The domain of a composite function f of g of x is the set of those inputs x in the domain of g, for which g of x is in the domain of f. How to? Given a function composition f of g of x, determine its domain. 1. Find the domain of g. 2. Find the domain of f. 3. Find those inputs x in the domain of G, for which g of x is in the domain of f. That is, exclude those inputs x from the domain of G, for which g of x is not in the domain of f. The resulting set is the domain of f, composed with G. Example 8. Finding the domain of a composite function. Find the domain of f, composed with g at x, where f of x equals 5 over x minus 1, and g of x equals 4 over 3x minus 2. Solution. The domain of g of x consists of all real numbers, except x equals 2 over 3, since that input value would cause us to divide by 0. Likewise, the domain of f consists of all real numbers except 1. So we need to exclude from the domain of g of x that value of x for which g of x equals 1. 4 over 3x minus 2 equals 1. 4 equals 3x minus 2. 6 equals 3x. X equals 2. So the domain of f, composed with g, is the set of all real numbers except 2 over 3 and 2. This means that x is not equal to 2 over 3 or x is not equal to 2. We can write this in interval notation as open parenthesis, negative infinity, 2 over 3, closed parenthesis, union, open parenthesis, 2 over 3, 2, closed parenthesis, union, open parenthesis, 2, infinity, closed parenthesis. Finding the domain of a composite function involving radicals. Find the domain of f, composed with g at x, where f of x equals square root of x plus 2, and g of x equals square root of 3 minus x. Solution. Because we cannot take the square root of a negative number, the domain of g is open parenthesis, negative infinity, 3, closed square bracket. Now we check the domain of the composite function. F, composed with g at x, equals square root of 3, minus x, plus 2. For f, composed with g at x, equals square root of 3, minus x, plus 2, and square root of 3, minus x, plus 2, is greater than or equal to 0, since the radicand of a square root must be positive. Since the square roots are positive, square root of 3, minus x, is greater than or equal to 0, and 3, minus x, is greater than or equal to 0, which gives a domain of, open parenthesis, negative infinity, 3, closed square bracket. B. Analysis. This example shows that knowledge of the range of functions, specifically the inner function, can also be helpful in finding the domain of a composite function. It also shows that the domain of f, composed with g, can contain values that are not in the domain of f, though they must be in the domain of g. Try it number 6. Find the domain of f, composed with g at x, where f of x equals 1 over x minus 2, and g of x equals square root of x plus 4. 1.4.5. Decomposing a composite function into its component functions. In some cases, it is necessary to decompose a complicated function. In other words, we can write it as a composition of two simpler functions. There may be more than one way to decompose a composite function, so we may choose the decomposition that appears to be most expedient. Example 9. Decomposing a function. Write f of x equals square root of 5 minus x squared as the composition of two functions. Solution. We are looking for two functions, g and h, so f of x equals g of h of x. To do this, we look for a function inside a function in the formula for f of x. As one possibility, we might notice that the expression 5 minus x squared is the inside of the square root. We could then decompose the function as h of x equals 5 minus x squared and g of x equals square root of x. We can check our answer by recomposing the functions. G of h of x equals g of 5 minus x squared equals square root of 5 minus x squared. Try it number 7. Write f of x equals 4 over 3 minus square root of 4 plus x squared as the composition of two functions. 1.4.6 Media. Access these online resources for additional instruction and practice with composite functions. Composite functions. http://openstaxcollege.org/l/compfunction . Composite function notation application. http://openstaxcollege.org/l/compfunc. Composite functions using graphs. http://openstaxcollege.org/l/compfuncgraph. Decompose functions. http://openstaxcollege.org/l/decompfunction. Composite function values. http://openstaxcollege.org/l/compfuncvalue.